Okay. I will talk very loud then. All right. Good evening, everybody. Welcome. Thank you, John. Welcome to our latest CHAP lecture, How the Search for Extraterrestrial Life Reveals Design in the Universe. I am Professor Leslie Keel. I teach history here at Porterville College, and I am the coordinator of CHAP. The Porterville Cultural and Historical Awareness, the Porterville College Cultural and Historical Awareness Program, CHAP, was organized in 2002 to enhance students' awareness of certain important aspects of our society to which they may previously have had little to no exposure. A theme is chosen by CHAP members each school year, and faculty members across campus are encouraged to integrate elements of that theme into their coursework. By subtly saturating students with information about the chosen topic throughout the year, the awareness of the entire campus community is elevated. Our theme for the next 2 years, fall 2024 to spring 2026, was voted on by over 200 students last year. That theme is Don't Stop Believing, all things belief systems, spirituality, religion, and secular humanism. We will be exploring the different ways humans have answered and wrestled with the big questions. Who are we and why are we here? I hope you will join us at our upcoming CHAP events, including our next lecture, titled Representing the Divine, Late Antique Jewish Art and Ritual. This is a rescheduled event from October with PhD candidate Rachel Schmid. Rachel's lecture will be on Thursday, December 5th at 7 p.m. right here in the PC Theater. I want to quickly thank our maintenance staff, CHAP committee, Roger Perez, Daisy Rodriguez, and President Monaraz for all their support, and making these events possible. Our speaker today is John Satko. John is a professor of physics and astronomy at Porterville College. He received his undergraduate degree in physics from the College of William and Mary and his master's degree in physics with an emphasis on astrophysics from the University of Colorado. He served in the U.S. Army as a health physicist and has been teaching at Porterville College since 2002. You're as old as Chad. When he is not teaching, John enjoys spending time with his wife and 4 children, running, speed cubbing, and studying biblical languages. Above all, he strives to live life to the glory of God through faith in Jesus Christ. As a quick disclaimer, the views and opinions expressed in this presentation are those of the speaker and do not necessarily reflect the views of Porterville College or its affiliates. Once Professor Satko is done speaking, we will open up for questions from the audience. Our event tonight will end at 8 p.m. Once the event is over, I will have proof of attendance cards for those who need one. And with that, please give a warm welcome to Professor Satko.
Thank you very much. By the way, when I told her about some of my interests, I may have spelled it wrong, I'm sorry. She said speed cubbing, and you're wondering what the heck is that. I meant to write speed cubing, so anyway. In case you're wondering. Yes, I keep one with me at all times. Thank you very much, Leslie. I am John Satko, professor of physics and astronomy at Porterville College. I've been here since 2002, as she said, and I love astronomy and physics. Just make sure the screen's up there. I've, since I was a child, been captivated. I was captivated by reading whatever I could about astronomy and science. And I remember as a little kid having a particular book I remember is the Star Wars question and answer book. So the movie Star Wars had just come out, the first one, and all this stuff I was learning about space as taught by C-3PO and R2-D2. And I loved reading the World Book Encyclopedia, just anything about space. I had a particular fascination with black holes, and I remember when it came out in the theater, I think it was 1978, Disney's The Black Hole. Terrible movie, sci-fi movie, but it was a black hole, and I was 7 years old or whatever, so it was awesome. You remember it, yeah.
Oh, yeah.
And I still love watching it even now, but oh my goodness. Anyway, I majored in physics in college, went through Army ROTC, was commissioned as a second lieutenant in the Army and worked in nuclear medical science. And after several years of that, I felt God's calling to become a teacher. So I went to graduate school at University of Colorado, and I got to do much with astrophysics. Particularly stars, Einstein's theory of relativity, black holes, and I love how this passion as a child I get to do as an adult. And sometimes when I'm teaching in class and I'm doing demonstrations, playing with stuff, sometimes I just comment to the students, I get paid for this. This is pretty neat, but it's what I always loved as a child. I love studying God's creation. Johann Kepler, he did most of his work in the early 1600s, is one of the founders of modern astronomy as well as modern science. He said, "The wisdom of the Lord is infinite, as are also his glory and his power. Ye heavens, sing his praises, sun, moon, and planets. Glorify him in your ineffable language. Praise him, celestial harmonies, and all ye who can comprehend them. And thou, my soul, praise thy Creator. It is by him and in him that all exist." For Johann Kepler, as well as others like Nicholas Copernicus, Galileo Galilei, their desire to learn about the universe was rooted in a desire to learn about the one who created it all and who holds it all together. In fact, modern science, science as we do it today, was developed by these men, among others. It was originally founded on a belief that a creator has written order into the universe and that order can be discovered by mere mortals. And in my life, worship of God has been studying the work of his hands, from very large galaxies far, far away to the very small atoms. I love to learn about the wonderful universe he has made and then give him glory by sharing it with others. And tonight I want to share with you a fascinating and relatively new field in astronomy called exoplanets, planets outside of our solar system. And one reason that it's fascinating is that it's intertwined with the search for life beyond Earth. And frequently I see a news article about a new planet discovered. And it's always, the news article at least, is always tying this discovery with the possibility of life. But in these news articles, the immediate jump to the possibility of life is very premature. It's, I think, irresponsible journalistic sensationalism to say we've discovered a planet, hey, and there might be life. But I'm going to talk to you about those issues tonight. We find that the universe, beyond the safety of planet Earth, is very hostile to life. And yet we have our planet that protects us from that hostility. Not only does Earth protect us from what is out there, such as, well, for one thing, there is a lot of deadly radiation that's out there. The Earth protects us from that, among other things. But it's highly conducive to having and fostering life. Everything about this planet, its geology, its atmosphere, its location in the solar system, its location in the galaxy, the characteristics of its sun and its moon, its gravity, which comes from its size, its mass, everything about it seems to be made for life. And not just the simple microbes that astronomers hope one day to find, but the vast diversity of species. Biologists have identified several million species of life on Earth, and outside of life, zero. So exoplanets, that's the main topic of today and the search for extraterrestrial life. When I was growing up, there were 9 planets. Maybe you remember them from grade school: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And if you're as old as I am, or maybe not that so old, you remember Pluto. And if you're also that old, this might be giving you a Brady Bunch vibe right here. Okay. So yeah, the 9 planets, now the 8 planets. If you go out tonight, there is setting in the west, because that's where things set, is Venus. And also Saturn is up there. Jupiter should be coming up over the mountains just now. And Mars will come up after midnight. So tonight we have 4 planets that you can see in the sky. And if you look to the west by the time we get out, or to the east, as we get out here tonight, there's going to be a very, very bright thing. Not the full moon, you know what the moon is, but anyway, a bright thing below the moon, and that is Jupiter. So tonight you have the possibility of seeing 4 planets, but 5. Just look straight down. So, all right, thank you. By the 1980s, astronomers had figured out that there were most likely many, many planets out there beyond our solar system. Now, they hadn't seen any yet, but they figured they should be out there. It's just that they would be so far away, they would be too dark to see at those great distances. But astronomers had a hope that one day we will find planets around the planets beyond our solar system. Then in the mid-1990s, the first planets outside of the solar system were discovered. Now, when I say the solar system, that is the sun and the planets that go around it, the asteroids and comets. Cosmically speaking, the solar system is our neighborhood. Planets outside of our solar system are ones that orbit around other stars. They're in other solar systems, other star systems. And so we call these exoplanets. Now, this is a picture of an exoplanet. The big blue thing is a star, but the red thing is a planet in orbit around a star. This particular one is 63 light years away, meaning if we see it in the sky, then it took the light 63 years to come across space to get to us. So if you're 63 years old, the light left it when you were born, and now here it is. When I started teaching at Porterville College in 2002, there were just a handful of known exoplanets. In fact, my first year teaching at the college, I didn't even mention exoplanets. Maybe I mentioned it briefly in a sentence to my students that, yeah, there's some other planets out there, but it really wasn't a big thing that we knew too much about. And then in the ensuing years, I realized, wow, this is a growing field. Well, as of a couple of weeks ago, when I looked up this information, we have discovered, astronomers have, I haven't discovered any, but we've discovered 5,780 exoplanets. I say they're confirmed exoplanets, meaning it's hard to tell. They're at such great distances, and I'll tell you about the techniques that we use, but we find something that we think might be an exoplanet, and then we have to do some observations. But we've confirmed 5,780 with 965 star systems that have more than one planet. And then there are another at least 10,000 possible exoplanets, meaning they found something that might be a planet, but they're not quite sure, and they're working on it. This is a picture of the nearest stars to us. So what you see is a bright light and circled, very tiny. I don't know. Oh, there it is. Okay. Wait, I can look at the screen. You're looking at that screen. I think right there, little red dot there, but it's with the red circle. That's a 3-star system. We generally, since ancient times, it's been called Alpha Centauri, but it's really 3 stars. The big bright light is actually 2 stars that are so close together that the telescope that took this picture couldn't resolve that it's 2 separate stars. But they're known as Alpha Centauri A and B. And then the nearest one, that little tiny red one, is Proxima Centauri. Now those are about a little over 4 light years away. They're our closest stellar neighbors. By the way, when I say stellar, that word just means, stars. So Proxima Centauri is known to have a few planets. There are at least 3 planets going around it. Put a little cursor on Proxima Centauri. And possibly 5 more. Now, it's worth noting that these are our closest stellar neighbors, so it's not that planets are hard to come by out there. The closest stars to us have a bunch of planets around them. By the way, Alpha Centauri B, which is one of these 2 stars, although you only see one, has a planet orbiting around it. Now, stars are very far away, and the planets that orbit around them are relatively very dark and small. I mean, you see how tiny in this picture here Proxima Centauri is, and it's a very, very bright star, and it's pretty close to us. Now imagine an even tinier planet in orbit around it, so these planets are hard to detect. So in a bit, I'm going to talk to you about the amazing techniques we use to find them. Astronomers are finding, though, as we look out into the heavens, that there are probably on average, about 1 planet per star in our galaxy. Some stars have many planets, some don't have any. Oh, and this, by the way, is kind of a zoomed-in artist's rendering of Alpha Centauri A and B, and they're in a tight orbit around each other, and then way off in the distance, Proxima Centauri. So probably on average, we don't know, but it's a good estimate, probably 1 planet per star. And there are about 100 billion stars in the Milky Way galaxy. And our galaxy, by the way, is one of probably about 1 trillion in the universe. But just in our galaxy, about 100 billion stars. So with 100 billion stars in the galaxy, I think it's reasonable to assume that there are about 100 billion planets somewhere out there in the Milky Way galaxy. Again, we've discovered more than 5,000 and several thousand candidates. And so that's the estimate that most astronomers tend to agree with. There are probably about 100 billion planets in this galaxy just waiting to be found. Now, we don't find planets by just seeing them. They're so far away that directly imaging them is pushing the limits of our current technology. In fact, the picture I showed you a bit ago with the big blue star and the red star, that's a very recent picture that pushes the limits of what we're able to do right now. Even in our own solar system. Hey, does anybody know what this planet is? It's in our solar system.
Neptune.
Awesome. Okay, yeah, Neptune. Even in our own solar system, the 8th planet, Neptune, was not discovered by anybody seeing it. Nobody looked through a telescope and said, oh, I see a planet. It's too far away and dark to do that. Rather, it was found by mathematics and the theory of gravity. The 7th planet, can anyone name that one? Uranus. All right, Uranus. Wonderful. So what happened when they discovered the 7th planet? This was about the time of the American Revolution. I think it was 1781, I think, when it was discovered. It wasn't where the mathematical equations said that it should be. So they saw Uranus up in the sky, and then they ran the equations, the physics equations of gravity, and they said, wait, the equations say Uranus should be up there, and it's right there. And they were wondering, why are the equations wrong? And then somebody got the idea, maybe there's a planet beyond Uranus that is gravitationally pulling on it. So they took that hypothetical planet and they said, okay, where would that planet be that would be having such an effect on Uranus? And then they pointed telescopes in that direction, and then they found it. They found Neptune. So that was in 1846. So they discovered Neptune by its effect, its gravitational effect on something else. And today we detect exoplanets by the effect that they have on their host stars, not by finding them directly with the telescope, but by what they're doing to the star they orbit around. So exoplanets will sometimes affect their star's motion, giving it a bit of a nudge or wobble. Sometimes the exoplanet will affect the light that we receive from that star. I just threw this up here to make you dizzy. All right, so what you're seeing in this simulation is the big thing is a star, and the little thing is a planet going around it. And what's really happening is they are in orbit around a common center of mass. So as the planet goes around the star, it has an effect on the star. It's making that star wobble around. And the closer the planet is to its star, and the more massive it is compared to the star, the more of an effect it's going to have. Jupiter, our largest planet in our solar system, has this little wobbly effect on the sun. So we can detect planets by measuring a change in the star's position in the sky. It's not going to be as dramatic as what you just saw, but there's a little wobble, and we can detect those tiny little wobbles. Now I can wobble back and forth like this. Can y'all see me wobbling? Okay, I can wobble back and forth, and this is the idea. And so, as seen from the back of the auditorium, there's an angle that you see me wobbling. The closer you are to me, the bigger the angle, but you see me wobbling at about 1 degree of an angle. So this is 90-degree angle, 45, 20. A 1-degree angle would be the width of your finger with an arm outstretched. So in the back of the auditorium, I think you see me wobbling about 1 degree. We don't see stars wobbling even that much. In fact, we see them wobbling a fraction of a millionth of a degree. It is the equivalent of watching something wobble by 0.5 millimeter out in Fresno. So at that distance, watching something wobble 0.5 millimeter, that is the kind of wobble that we detect in stars. It's very, very small. So it's very hard to detect. And this method is best for finding nearby stars with a massive planet. Now nearby, because you think just with me wobbling, you guys up front can see me wobbling more than the people in the back, and someone a mile away probably wouldn't even detect me wobbling. So the nearer the star is, the better. And the more massive the planet, the more of a wobble effect it has on the star. But if the star is really far away and if it's a low mass planet, there's not going to be much of a wobble and our instruments have difficulty detecting it. So there is a bias towards finding massive planets around nearby stars. Another method we use is called the Doppler method. Now, this is good for finding when a star is wobbling towards or away from you. If I'm in direct line of sight of you, you don't see me wobble. I mean, you see me doing this awkward motion, but you wouldn't detect so much of a wobble, but we use the Doppler effect. Most of you have heard a Doppler shift with sound waves at some point in your life, an ambulance siren, a car horn, the ice cream truck with the music going. Sometimes it sounds out of pitch, too sharp or flat. Well, it's because the siren, the ice cream truck, whatever, it's coming towards you and the frequency of the sound waves goes up. And when it's going away from you, the frequency goes down. And it works the same with light waves. So what this diagram shows, can you see my cursor? Good, okay, is here we have a star and a planet that we can't even see going around it. But the star, based on where the planet is, the star is going around in a tight circle. And from the perspective of Earth, Earth is at the bottom of the screen. So when the star is coming towards us, the light waves that we see, they go up slightly in frequency. And when the star is going away from us, they go down in frequency. So the frequency of the light keeps modulating to high frequency and low frequency, and high and low, and that's what's called the Doppler shift. It's a way of seeing wobble in a star, not side to side with reference to us, but going back and forth. And this is how the first exoplanet was discovered. I wrote on this slide, the first extrasolar planet. It means exactly the same as exoplanet, but back then in 1995, this is something that happens with science. When something is a brand new field of science in its infancy, they don't know what to call stuff. Someone comes up with a label and then later they say, we don't like that word, let's change it to something else. Well, back in 1995, they were called extrasolar planets, planets beyond our solar system. Means the same thing as an exoplanet. Okay, so Doppler shifts of a really faraway star called 51 Pegasi revealed that there was a planet going around it every 4 days. So every 4 days, this star came towards us and away from us and towards us and away from us. And given that it was only 4 days, that means that the planet was really close to its star. And again, this was the first exoplanet to be discovered around a sun-like star. That was in 1995. By the way, if you care, up in the sky, here's Cygnus the Swan and Vega. Those are stars that right now they're probably about there if you go outside. And in the constellation Pegasus, it's a star that it's very dark. You wouldn't be able to see it, at least without a telescope. Okay, so methods for exoplanet detection. I've told you about two of them. The astrometric method, which is good for seeing wobbling back and forth, left and right. There's the Doppler method, good for seeing wobbling forward and backwards. And these are both good for finding massive planets that are near to us and close to their host stars. There's a third method that we use called the transit method. Now, a transit occurs when a planet crosses in front of a star. So again, imagine we see the star up there, but we don't see the planet. Now here you see with my cursor the planet, and it moves in front. Here it is in position 2 and position 3. As it moves in front of the star, the light that we see goes down just a wee bit, maybe 1%, which is representative of the surface area that the planet is covering of the star. The light of the star goes down a bit. And then however long it takes the planet to go around the star, then we see a little dip in the light. And then all the light is there again. And then a little dip in the light. But not only that, the planet itself gives off a little bit of infrared radiation that we also detect. And when the planet goes behind the star, there's a little dip in the infrared radiation. So we look up in the sky with very sensitive, precise equipment, and we see this star, and its light dims just a little bit. And then the infrared goes down a little bit. And then the light dims just a little bit. and then goes up. And then the infrared dims a little bit, and that tells us, that's a planet. We see there is a planet moving in front of the star. And notice, in all these methods I've said so far, we never actually see the planet. We just see its effect on either the star or the light that we receive. So these are the three main methods, indirect methods, of detecting exoplanets. And there is a strong bias for finding stars that are planets that are massive, that are close to their stars, and that are large and close to their stars. And then there's also, just recently in the past few years, direct imaging. So we are actually now able, it's like on the cutting edge of our technology, but able to see stars, and so, planets going around other stars. And here's a star system with a few planets. The star in the middle, they've blocked it out with this circle here, so the light of the star doesn't overwhelm the relatively darker planet. So they've blocked out the star. But here you see somebody's kindly labeled B, C, D, and E. I can't remember where A is. It's probably like behind the star or something like that. But anyway, here we see images of 4 planets going around a star. And then there's the picture I showed you a bit ago of a star, the blue thing with a little red planet going around it. So now we are having the ability to actually take pictures and see with our eyes these planets. And by these methods, which astronomers continue to perfect, we found, as I said before, over 5,000 exoplanets. And these thousands of exoplanets have great diversity of size, mass, distances to their stars, and chemical composition. But what we find is that none of them is like Earth. The universe is not like on Star Trek or Star Wars, where you can land on the next planet up ahead, and the air is just right, and the gravity's just right, and the temperature is just right, and the air pressure is just right, and everything's just right. The radiation levels are just right. Let's just beam down to that planet. Take every important member of the crew and the guy in the red shirt. Anyway, it's not like that. The only difference with those planets in Star Trek is that the sky is pink. That's how it was in Star Trek. If you read the book The Martian, or if you saw the movie that came out in 2015, you got a pretty good sense of how hostile the planet Mars is for life. And of all the planets beyond Earth that we have explored, Mars is actually the tamest, the most likely where someone could survive, like Mark Watley did. Earth is uniquely wonderful. That's not Earth. That's Earth. Earth is uniquely wonderful. In God's grace and provision, He's made for us a planet that is just right for us to live and enjoy life. And it's been called the privileged planet. There's so much that is just right about Earth for life. People sometimes say it's such a vast universe. Certainly there must be many Earth-like planets. The term Earth-like is very non-specific. A planet can be like Earth in size. It can be like Earth in mass, maybe have an atmosphere, maybe have a solid surface to stand on. But I think when people use the phrase Earth-like, they're really imagining a planet that has the qualities of Earth that are conducive to life. Now, in contrast, the planet Venus is very Earth-like. It's about the same size of Earth. It's about the same mass. It even has carbon dioxide in its atmosphere, but it is very hostile to life. The atmosphere is very thick. On the surface, its atmospheric pressure is 92 times what you're experiencing right now. So that any space probes that we have sent to the surface of Venus have been crushed within, I think the longest lasting one was like about an hour before it just got crushed. If you were transported to Venus, you'd be crushed instantly. Imagine the air pressure would be 1,300 pounds pressing on, not just on your body, but on every square inch of your body. 1,300 pounds, you'd just be crushed in. So Venus is even though it's very Earth-like, it's very hostile for life. The thick carbon dioxide atmosphere, combined with Venus's proximity to the sun, makes it very hot. It's over 800 degrees there. Whether daytime or nighttime, it doesn't matter. There's no relief from the heat. So we won't be colonizing Venus anytime soon. When we are looking out there into the cosmos, looking for a planet or planets that may be hospitable for life, we ponder the question, what is it about Earth that allows life to form and exist here? And then we can narrow our search a bit. Now, the astronomers' interest in this, why would we care to find these planets? Well, for one thing, just for the sake of exploration, just for the sake of learning about our universe. But also, more practically, people are, well, again, for scientific exploration, interested in, is there life out there? And where can we find that life? More practically, maybe we're looking for a second home eventually. Where could there be a planet where we might want to settle? This is the Arecibo radio dish in Puerto Rico. In 1974, a group of astronomers at Cornell University sent a famous Arecibo message, is what it's called. It's a radio message carrying basic information about Earth and mankind to M13, which is a beautiful globular cluster of stars. It's a cluster made up of about 1 million stars that are all orbiting around their common center of mass. It's we see it through the telescope, just a beautiful, looks like a big puffball in the sky where you can see all these stars. And so they sent this radio message to alien civilizations to tell them about us. Now, M13 is about 25,000 light years away, so this message that they sent will take 25,000 years to arrive. It was meant as a demonstration of human technological achievement back in 1974, rather than a real attempt to enter into a conversation with extraterrestrials. And for marketing purposes, it was great. The whole point was to say, look, not look aliens 25,000 years from now, but look world, look what we can do, look what we have the ability to do. And for marketing purposes, to excite this conversation about astronomy, it was awesome. Scientifically, though, it was terrible. As you think about sending messages, the idea we're sending messages to these, or a message to these millions of stars, certainly there's life out there. But this is about the worst place to look for life. The idea here is that there's a huge population of stars, maybe there's life there. But a globular cluster of stars would be very inhospitable for life. We on Earth have one sun. Imagine having 1 million suns all crowding up the sky. There would be such great gravitational instability, such deadly radiation, the occasional supernova popping off, and so you're not going to find life over there. So if we are to one day find life out there in the universe, or perhaps even a second home for mankind, or third, what sorts of places should we be looking at? That's what astronomers are interested in. What places should we be looking at? What does a planet need in order to harbor life? So I want to talk to you about some of those things. Astronomers can't just be randomly looking all over the universe. It's a big universe for, is there a planet anywhere? So we look for, where should we be looking? Well, for one thing, a planet that is good for harboring life needs to be around the right kind of star. First of all, it needs to be around just one star instead of a multitude of stars like a cluster, because it needs to have a stable climate. If you're in a planet orbiting around 3 stars, there's times when you're close to 1, times when you're close to 2, times when you might be in the middle of the 3, and it would be very unstable for the climate and probably unstable radiation. So it needs to be around one star, and particularly the right kind of star. So let's talk about our sun. The sun is in our sky. It gives heat, light, and other forms of radiation necessary for life, and it gives it in the right amounts. Did you see that little thing that popped up there with the arrow pointing to it? That's the Earth. That's the size comparison of the Earth compared to the sun. But the sun is so perfect. It provides everything that we need just right. The sun generates light and heat by nuclear power. It's a mind-bogglingly immense amount of light and heat. In the time it takes to say the words nuclear power, the sun has put out more than 1 million times. I'm sorry. I'm going to change that number. It puts out about 500,000 times the annual energy consumption of the entire world, just in the time it takes to say nuclear power. The light and heat are necessary for all life on Earth. The sun gives the light needed for photosynthesis in plants, which we all need. And yet the sun itself, as stable as it is of a star, it's very turbulent. It's a very cataclysmic environment with huge storms much larger than the entire planet Earth. And so here's the sun with a magnetic storm coming from it. There's the approximate size of Earth in comparison. There's a storm you don't want to be anywhere near. Yet as turbulent as the environment is, the sun is a remarkably stable star. And we need that for life. Not all stars are like that. The sun is an incredibly stable star when we compare it with other stars. Other stars are more prone to flares of dangerous radiation, instability in the amount of energy they put out. Imagine if the sun, one day it gave out 10% more light and then 10% less, that would be a mess for life. Our sun has the stability that's necessary for life on Earth. Earth is the right distance from that star. Now this picture here shows the habitable zone. I think a lot of people have heard about this. In fact, as I walked in the room today, I heard two people talking about the habitable zone. The idea is that in order for there to be life on a planet, it needs to be a certain distance from that star. It's often called the Goldilocks zone, not too hot, not too cold. If it's too close to the star, then you're not going to have liquid water. It'll all be boiled away. If it's too far away, there's Earth, by the way, in that habitable zone. If it's too far away, the water on the surface would be frozen. But you necessarily need, for life as we know it, as biologists understand life, you need liquid water. And so it needs to be in the star's habitable zone. And so for a star like our sun, it's at about this distance. Now other stars, we go to cooler stars, orange and red stars, and they have habitable zones. But because they're cooler in temperature, you have to be closer to it in order to get the proper amount of warmth. Well, the problem is, and this gets into what I was talking a few minutes ago about the right kind of star, you get too close to those stars, so the red and orange stars, and you're so close where there can be liquid water, but there's a lot of dangerous radiation and flares that come out. So we're not going to find life, I don't think, around these cooler red or orange stars. You need to be a safe distance away and yet still be warm enough to have liquid water. Pretty neat. Another thing about if a planet is close enough, like to be close to these red stars, if a planet is close enough to the star, it's going to be in something called a gravitational lock, which means as it goes around the star, the same face of it will face the star each time. It's as if so if the star were right here and I'm the planet, I face the same face to it each time instead of rotating around. Well, when we rotate around, we go around the sun, we get 12 hours of day, 12 hours of night, something like that, depending on the season. Well, you would just, on these planets, have constant exposure to the sun all the time on one side, and constant non-exposure to the sun all the time on the other, and that's not conducive to life either. There would be very, very hot on one side, very cold on the other side. Planet Mercury is like that. Mercury, the closest planet to the sun, and a lot of people know that, think it's the hottest planet. Not really. There's the daytime side of Mercury, and always daytime side. It changes eventually through the course of the year. But so it's about, on the surface of Mercury, about 800 degrees. But on the nighttime side, which just stays shrouded in night for a long time, it's about negative 300 degrees Fahrenheit. So it's either very hot or very cold on Mercury. So my point is, you need to be around a star that you can be far enough away from it, and you need to be in this thin Goldilocks zone. The Earth has an atmosphere necessary for life. Oxygen, carbon dioxide, nitrogen, water vapor, all these things necessary. And the atmosphere blocks us from harmful radiation. There's a lot of deadly radiation out there that astronauts who go up there, they have to be shielded against. We are shielded by our atmosphere from this radiation. And yet, the atmosphere lets down visible light so that we can look up at night and see what's out there and give glory to the Creator. If you go to the hospital and get an x-ray, they give you a lead shield to protect your body from the harmful x-rays. That's what our atmosphere does. It's our lead shield. The x-ray tech always steps out of the room into a lead-lined booth, but, leaving me out there. God has given 60 miles of air to act like our lead shield, protecting us from the radiation that's out there, protecting us from all the harm that's out there. Now, a planet that can harbor life would also need a well-designed synergy between the atmosphere and the liquid water. It's not enough just to have liquid water on the surface. Life on Earth doesn't really merely rely on liquid water, but on the atmosphere's ability to hold water vapor. There needs to be evaporation, which is liquid water going up into the air. There needs to be precipitation, which is water coming from the air back down to the ground. We need to be in the right type of galaxy if there's going to be life, because different types of galaxies are going to have the planets, the stars in them, different orbits, unstable amounts of radiation. Needs to be in the right type of galaxy. This is a galaxy you see in the picture like ours, a spiral galaxy. And we need to be in the right part of the galaxy. Astronomers have found that it can't be anywhere in the galaxy, but not too close, it's a Goldilocks zone. It's called the galactic habitable zone. So not too close to the center, where there's going to be a lot of deadly radiation from an excess of supernovas, explosions of stars, but not too, where's my cursor? There it is. Not too far from the center, because you need to have enough, these supernovas, they are good for life because it's in these supernovas or in stars where heavier elements are created that are necessary for life. And so astronomers have found that if we're looking for a planet where there might be life, it needs to be in a spiral galaxy, which is good, that's ours, and it needs to be in the right part of the galaxy. The question then arises, how many habitable planets should we expect to find in the universe? Frank Drake was a 20th century astrophysicist and astrobiologist who developed the Drake equation in 1961, which attempts to quantify the number of life forms in the universe that could potentially be discovered. Now, Drake designed and implemented the message that we sent from the Arecibo radio dish. The radio transmission. He came up with this equation that summarizes the main concepts that scientists need to contemplate when considering the possibility of finding life out there. And it's more of an approximation than a serious attempt to determine the precise number, but at least it's a starting point to get the conversation going. We can use Drake's principles and come up with, I'll make up a modified version of his equation. I'm going to get mathy on you. I hope you're okay with it. All right. So as we think about how many planets should there be out there that should we expect to find out there that are suitable for life? And it goes like this. N is just the number of planets we should expect. You start with the number of planets that we estimate to be in the universe. That's a whole lot. But then we're going to cut that down by multiplying it. That's a multiplication sign, by the fraction of those planets that have a single star that is like our sun. So that's going to cut down that population quite a bit. Multiply that by the fraction that are in the star's habitable zone. That's going to cut it down even more. Multiply that by the fraction that are in a spiral galaxy. It cuts it down even more. That are in not just a spiral galaxy, but the galactic habitable zone. And every time you multiply by this fraction, you're cutting down the possibilities, how many planets you can expect. The fraction that are going to have liquid water. Not just be in the habitable zone, but actually have liquid water. The fraction that have a suitable atmosphere, the fraction that have a suitable water cycle, etc. Astronomers have come up with, I've put like 8 on the screen there, astronomers have come up with about 300 parameters that they say a planet has to have all these things just right in order to have life, at least life as we understand it. I want to play a game with you, please. A Drake equation game with you. I'm looking for, so just like in astronomy, we're looking for the right planet with all the right characteristics. I'm looking for in this room the right person. I mean, you're all the right people, but with these certain characteristics I've come up with that fits these parameters. A female born in November, left-handed, drives a Toyota, at least 5'11", age 40 to 44, last name starts with the letter V. I've done the math, and I think I've just described a 1 in a billion girl by those probabilities. So here's how the equation works. Of the population, roughly 1/2 female, and that's going to be rough. So will you please play this game with me? I would like everybody, will you please raise your hands? Everybody raise your hands. Don't worry, you'll be putting it down before long. Okay, so only if you if you satisfy this criterion, put your hand down. Good, I get to put my hand down. So if you're female, leave your hand up, and everyone else, okay, can put their hands down. Okay, now, left-handed. So if you're right-handed, put your hand down. If you're left-handed, so we've still got left-handed females are the only. I'm going to say incorrect. Okay. Adriana, are you left-handed? Oh, keep your hand up. I'm not saying incorrect to you. Okay, you're left-handed. Okay, Bonnie, you're left. Okay, left-handed. Okay, got your right. Okay, cool. Left-handed. Okay, drives a Toyota. Put your hand down if you don't drive a Toyota. You drive a Toyota? What kind? Camry. Awesome. Okay, love those. Okay. At least 5'11". Are you still there? You're 5'11". All right. Oh, okay. Well, I didn't want to go to the next one, but you've driven me to it. Age 40 to 44. I didn't want to ask. Last name starts with the letter V. Okay, so no more hands are up, right? Okay. Oh, I'm sorry. Born in November. Well, too late now. So, all right. So, point is, there's nobody left. Now, the probabilities, here's how it works. We start with everyone in the room, and then that gets cut roughly in half. I didn't do a survey as y'all entered in what percentage are male and female, but roughly a half. Born in November, 30 over 365. You can argue with me about leap years, but that's about right. Left-handed, about 1 in 10. Drives a Toyota. I looked it up. I Google searched some of this. About 1 in 10, at least in America, at least drive, if not own a Toyota. And then you're saying, I'm not sure. I want to disagree with you about those probabilities. That's okay. You can do that. When astronomers do the same thing, looking for all these criteria of planets, we don't know the probabilities either. So we make assessments. So we can argue about these probabilities, but they're in the ballpark, I hope. At least 5'11". Yes, I did some math with that. 15 out of 10,000 females. Age 40 to 44, Google search again. 6%. Last name starts with the letter V, at least using the Roman alphabets, English, Spanish, French. I think I got about 26 out of 1,000. And that comes out to be the probability roughly 1 in a billion. I was expecting no one in this room to be left with their hands up. In fact, if I had done this over the entire United States, I would expect 0. Maybe 1. If we surveyed the entire world population, I would still expect not too much more than 0 or 1. Now let's bring it back to astronomy, what this has to do with it, and the search for habitable planets. Astronomers have come up with over 300 criteria that are necessary for a planet to be habitable, that is, to be able to support life. I came up with here, you see on the screen, those 7 criteria. Astronomers have come up with about 300 with much lower fractions, much lower probabilities than these. The probability of a random occurrence, just it all randomly coming together, of all 332 parameters, astronomers, it varies when they do the Drake equation depending on what your assessment and guess of the probabilities are, but typically something like this, 1 in, not a billion, but 10 to the 304th power. That means a 1 with 304 zeros after it. To a physicist, that's 0, basically. 0 probability. Now, the maximum number of planets that astronomers think is in the universe, an estimate of about 10 to the 23rd power. That's a 1 with 23 zeros after it. And that's a ballpark estimate. It could be 10 to the 24, 10 to the 25. But this is what most astronomers agree with, 10 to the 23rd. And so, it's a lot of planets out there. But the probability of any such planet having everything just right for life on it is so minuscule that it doesn't matter there are this many planets. The probability is so low that it overwhelms that number of planets. So the number, using the Drake equation, the number of planets that we could possibly find that could have life on them is, and you see the math there, the number of planets times that probability, and it's about 1 in one with 281 zeros after it, which is basically 0. By randomness, no such planet should exist in the universe. And this doesn't even get into the question of where we should find life. I haven't even talked about the biological aspect of whether or not there is life on such a planet. I'm just talking about finding a planet that is a good host for life. 0. And yet, here we are, defying the odds. And not only do we have a very privileged planet that is able to have life, but we have life in abundance on this planet. From Earth's history, we learn that when Earth first formed, it was very inhospitable for life. But then conditions changed, and within a very short time, very, very short time, life appeared. Earth has all the right conditions that make it perfect, not only to have life, but to do it and have abundant diversity of life. Earth is the right distance from the right kind of star. If it were much closer, too much farther away, we could not have liquid water in abundance. Or we might get a lot of these radiation flares. Our sun is very stable in the amount of radiation it emits. So it allows for us to have a stable climate. The Earth is in the right part of the galaxy, the right part of the right kind of galaxy. So there's enough supernova activity to have elements necessary for life that's produced in stars, but not so much supernova activity that Earth is overwhelmed with radiation, because those things put out a lot of deadly radiation. The planet Earth has the right size, it has the right mass, it has the right atmospheric density, it has the right atmospheric composition, the right amount of tectonic activity. All these things are necessary for life on Earth. It has the right interaction between the atmosphere and the groundwater. The tilt of Earth's axis is related to all of that so that we have seasons. The abnormally large moon that orbits the Earth serves to stabilize the tilt of Earth's axis by its gravitational pull. And the list goes on. When you go outside tonight, there's a very big full moon out there. So go out and appreciate that life on Earth depends on the stability that that moon brings to Earth's tilt. And by the way, when you're out there looking at the moon, down below it is a very bright looking thing. Looks like a star, it's Jupiter. The Earth is just right for life. And all of this shouts the existence of a creator who made the earth, who made us. God has infinite wisdom and creative power. He's made a universe that has a great variety and diversity of planets, but only one, it seems, is just right for life. It's just right for us. And I'm reminded of the famous hymn, "How Great Thou Art." O Lord my God, when I in awesome wonder consider all the worlds thy hands have made, I see the stars, I hear the rolling thunder, thy power throughout the universe displayed. In the 16th and 17th century, Johann Kepler, Nicholas Copernicus, Galileo Galilei, and many others did not know about exoplanets. But they saw enough by looking up to the skies and by looking at the world around them. They recognized that this is all made by a creator. And not only did he make it, but he made it so that it could be explored, so that the world and the universe could be understood, so that the laws of physics that govern how the universe operates could be understood by intelligent beings, or not so intelligent beings, that he created. And those men of the Renaissance who were the pioneers of modern science and astronomy were in awe. And they wanted to learn more so that they could honor and worship their Creator. Much of the New Testament of the Bible was written by men who were eyewitnesses to the life and ministry of Jesus Christ in the first century. And these letters were copied, passed around, and read by other eyewitnesses. These first century Christians had a strong commitment to the truth. And if any of these accounts had been invented or even embellished, then there was a great multitude of witnesses who would have said, no, don't write that down, don't spread that. And I believe that these letters were accurate representations of what happened, and having studied the manuscript evidence myself, I believe they've been accurately passed down to us through the centuries, so that we hold in our Bibles a reliable witness to what happened in the life of Jesus. His miracles demonstrated his command over the laws of nature and over the universe. It says that he turned water into wine. He healed paralytics, those having all kinds of sicknesses. Crowds followed him wherever he went just to see all this. He calmed deadly storms. And as I ponder the universe that we learn about through our study of astronomy and astrophysics, as I continue this lifelong pursuit of learning about the countless stars, the galaxies, the planets, the black holes, and the physical principles of how all they operate, I'm compelled to marvel at the one who made it all. God's word tells us that by him all things were created in heaven and on earth, whether visible and invisible. We're told, for God so loved the world that he gave his only Son, that whoever believes in him will not perish but have eternal life. And whoever believes in him is not condemned, but whoever does not believe stands condemned already, because he has not believed in the name of God's one and only Son. For every one of us, there are only two possible destinations, eternal life or eternal condemnation. And the reason is, as we're told in Romans, all have sinned and fall short of the glory of God. And the wages of sin is death, but the gift of God is eternal life in Christ Jesus our Lord. And God demonstrates his own love for us in this. While we're still sinners, Christ died for us. So you might be asking, how can I get this eternal life, this relationship with the one who made this all? It says, if we confess our sins, he's faithful and just and will forgive us our sins and purify us from all unrighteousness. Jesus said, I am the way and the truth and the life. No one comes to the Father except through me. He didn't say, there's your truth and there's my truth and it's all good. He said, I am the truth. And if you don't know Jesus, if you haven't trusted him as the one, the only one who can save you from condemnation, he calls you to him. He says, come to me, all who are weary and burdened, and I'll give you rest. And I'd love for you to come talk to me afterwards and I can share with you. I study astronomy and physics because through those disciplines that I first learned about when I was a kid, I see the creative power of God. And people would call me a man of great faith, but from what I've seen in the universe, I have no other choice, no other conclusion to draw than that this universe has been created. And my observations and rationality compel me to recognize him and to admire and worship our Creator. Thank you very much. Is this where I take questions?
Well, it is after 8 o'clock, and security will get cranky with you.
Oh, okay.
So, now we normally would have questions, but we started a little late. So I know that Professor Satko will be up here for questions. I hope that most or all of you will join us on December 5th. I do want to make a quick correction. I said that that event would be here in the theater. It's actually going to be in the Forum on Thursday, December 5th, to hear from Rachel Schmid on Jewish art and antiquity. Yes?
Is there going to be parking?
It will also be parking in the back at that point, I believe. So we are at the whims of the construction gods. So I apologize for that and for the confusion on that. But the parking will be in the back. The Forum is also in the back, though. So we also have a full lineup for next semester. We have 6 events already in the works. So keep your eyes out for information on those. And thank you all for coming. And another warm round of applause for our
Thank you. I greatly appreciate y'all coming out tonight, and I greatly appreciate y'all the walk you had to take and from the parking, so sorry about that. I hope it was worth it. Anyway, thank you very much. If you want to stick around, you can.
I have a question.
Yeah, sure.
Okay, so the moon, what does that, why does it change like people's behavior when you're on Earth when there's like a full moon? People like to go crazy.
There, you just answered it. People like to go crazy. It doesn't. There's kind of, maybe it's like a placebo effect. I think, people say, look, people are acting crazy. It's a full moon. But actually, people are always acting crazy. You just notice it more because you know to notice it when it's the full moon. But it doesn't. Yeah. Anyway, if y'all want to talk anything extra, I'm going to go off mic here and just talk with y'all if you want to. Thank you very much.
And we have a